Welcome everyone. Today we'll explore one of the most fundamental algorithms in deep learning, which is backpropagation. Backpropagation is essential for training artificial neural networks. Without it, deep learning models wouldn't be able to learn from data effectively. This algorithm is designed to minimize errors by systematically adjusting the network's weights and bias. But how does it work? It all starts with error propagation. When a neural network makes a prediction, we compare the output to the actual target value. If there's a difference, which is an error, the backpropagation algorithm calculates how much each weight contributed to that error. It then adjusts the weights in the opposite direction of the error gradient, ensuring the model improves over time. This process is repeated thousands, even millions of times during training. Modern deep learning models, such as those used in image recognition, natural language processing, and even self-driving cars, rely heavily on backpropagation. It enables them to generalize from data and make highly accurate predictions. Today, we will break down the backpropagation process, understand why it is so effective, and explore how it shapes the future of AI. Before we dive deeper into backpropagation, let's first understand the fundamental structure of a neural network. A neural network is inspired by the human brain. It is composed of three main layers. First, input layer. This is where raw data enters the network. For example, in an image classification task, each pixel of an image would be an input neuron. Second part is hidden layers. These layers contain neurons that perform mathematical transformations on the input data. The more hidden layers as a network has, the deeper its learning capacity. Final part is output layer. This layer provides the final prediction, such as classifying an image as a cat or dog. Each layer consists of neurons, which are the basic computational units. These neurons are interconnected, and the strength of each connection is determined by weight. During training, these weights are adjusted so that the network can make better predictions. Additionally, each neuron uses an activation function. This function introduces non-linearity into the model, allowing it to learn complex relationships with data. If we didn't have activation functions, neural networks would behave like simple linear regression models, unable to handle more intricate patterns. Understanding this structure is crucial because backpropagation works by modifying these weights and biases to reduce errors, ensuring that the network makes better predictions over time. When training a neural network, our ultimate goal is to minimize the error between predictions and actual values. But how do we measure this error? We use a cost function, also known as a loss function, which tells us how far off the network's prediction are from the true values. The network's learning process revolves around reducing this cost function. There are different types of cost functions depending on the task. First is mean scale error, which is MSE, commonly used in regression problems. It calculates the average scale difference between predicted and actual values. Scaling the errors ensures that the larger mistakes are penalized more. Second one is cross entropy loss. It is often used for classification tasks, and this function measures how different two probability distributions are. It is widely used in deep learning models for tasks such as image classification and speech recognition. Once the cost function is computed, the network adjusts its weights using gradient descents to minimize this value. Over time, as the cost function decreases, the neural network becomes better at making predictions. Cost functions are an essential part of neural network training, guiding the entire learning process. Without them, the model wouldn't know how well it's performing or how to improve. In order to minimize the cost function, we need an optimization method. One of the most widely used methods in deep learning is gradient descent. Gradient descent is an iterative algorithm that adjusts the weight of the network by computing the slope or gradient of the cost function. The key idea is simple. If the slope is positive, we need to decrease the weights. Otherwise, if the slope is negative, we need to increase the weights. The size of this adjustment is controlled by a parameter called the running rate. Choosing the right running rate is critical because if the running rate is too high, the model might oscillate around the optimal solution without ever converging. Otherwise, if it's too low, training will take an extremely long time. One useful way to visualize gradient descent is to think of it as descending a mountain. The goal is to reach the lowest point, the minimum cost of the cost function. If our steps, same as learning rates, are too large, we might overshoot the target. If they are too small, progress will be painfully slow. Gradient descent is the backbone of many machine learning algorithms, allowing neural networks to systematically reduce errors and improve accuracy over time. Now that we understand gradient descent, let's talk about backpropagation, the algorithm that makes it efficient. Backpropagation is a method used to update the weights in a neural network by propagating errors backward from the output layer to the input layer. But why is this necessary? When a neural network makes a prediction, we calculate the error at the output layer using a cost function. Backpropagation then determines how much each weight contributes to that error and adjusts them accordingly. This is done using a mathematical technique called the chain rule, which helps compute derivatives in multi-layered systems. The process works as follows. First, the network makes a prediction through forward propagation. Second, the error is computed using the cost function. Third, the algorithm calculates the gradient of this error with respect to each weight. Finally, the weights are updated in the direction that reduces the error. Without backpropagation, training deep neural networks would be nearly impossible because we wouldn't have an efficient way to compute these weight updates. This algorithm revolutionized deep learning, making it feasible to train models with millions or even billions of parameters. To gain an intuitive understanding of backpropagation, let's break it down by step by step. Imagine a neural network as a system of interconnected highways. Each road has different levels of traffic, just like different weights in a neural network having very levels of importance. Backpropagation helps us determine which roads, such as weights, are causing the most congestion, which is error, and adjust them to make traffic, which is learning, more efficient. Mathematically, we calculate gradients for each weight. These gradients tell us how sensitive the cost function is to a particular weight, and how much a small change in the weight will affect the overall error. And key insights from this process include first, larger gradients mean a weight is a bigger impact on the error. These weights require larger updates. Otherwise, smaller gradients means a weight has a minor effect. Adjustment will be smaller. By continuously fine-tuning the most influential connections in the network, backpropagation ensures that training progresses efficiently. This method enables deep networks to learn complex patterns in data, from recognizing faces in images to translating languages. Let's go through the step-by-step process of backpropagation to understand how it actually works in training a neural network. First part is forward propagation. First, input data flows through the network. Each neuron receives inputs, processes them using weights and activation functions, and passes the output to the next layer. This continues until we reach the final prediction. Second part is error calculation. The prediction is compared to the actual value, and the error is calculated using the cost function. This tells us how far off the network's prediction is. Third part is gradient calculation. The backpropagation algorithm computes how much each weight contributed to the error. This is done using direct derivatives and the chain rule. Last part is weight update. The gradients are used to update the weights, moving the network in the direction that reduces the error. This process is repeated thousands or millions of times as the network learns. Over time, the weights settle into values that minimize the cost function, allowing the neural network to make accurate predictions. So far, we've discussed gradient descent, but there's a challenge. When dealing with massive datasets, computing the gradient over the entire dataset in each step is computationally expensive. This is where mini-batch stochastic gradient descent, named as SGD, comes in. Instead of processing the entire dataset at once, mini-batch SGD splits the data into smaller batches and updates the weights using only a subset of data at each step. This offers several advantages. First, it can make faster training. Since fewer computations are performed per update, the new network trains more quickly. Second part is better generalization. By introducing some randomness into weight updates, the model avoids overfitting to specific examples. Final part is reduced memory usage. It is ideal for large datasets that cannot fit into memory at once. However, there are some trade-offs. Minibatch SGD introduces some noise into the updates, meaning that the path toward the optimal weights is less direct. Choosing the right batch size is important. A small batch size increases variability, while a large batch size behaves more like traditional gradient descent. Despite these trade-offs, mini-batch SGD is widely used in deep learning because of its efficiency and scalability. Propagation is not just a theoretical concept. It plays a vital role in cutting-edge AI research and applications. Some of the most significant advancements in recent years include, first, development of large-scale AI models. Models like GPT-4 and PLM demonstrate the power of massive neural networks. These models contain billions of parameters trained using backpropagation to understand and generate human-like text. Second is multimodal AI. Modern AI systems can process text, images, and audio simultaneously, allowing them to perform tasks like image captioning and speech-to-text conversion. Third part is energy-efficient AI. Training deep networks is computationally expensive, so researchers are working on model compression techniques like DistilBart or MobileNet, which reduce the number of parameters while maintaining performance. Last part is medical application. Backpropagation is used in medical imaging, helping AI models to detect disease in X-rays, CT scans, and MRI images with high accuracy. These advancements highlight how backpropagation continues to drive AI innovation, shaping industries from healthcare to autonomous systems. To summarize, backpropagation is the foundation of modern deep learning. It allows neural networks to learn by adjusting weights based on error propagation. It has enabled groundbreaking advancements in AI, from large-scale language models to medical diagnostics. As AI continues to evolve, researchers are developing more efficient learning algorithms to improve speed, accuracy, and scalability. So, what's next for backpropagation? Future research may lead to more biologically inspired learning methods that mimic how the human brain processes information. Faster, energy-efficient training techniques to reduce the environmental impact of AI. Next, better understanding of deep learning's decision-making process, making AI models more interpretable and trustworthy. Right. This is all for today. Thank you for your attention.